Hello Calculus fans, I thought I would make a little video to supplement something we're doing in Calculus 2. We're starting to do areas between curves. In the sections to come we're going to be doing volumes. And a lot of it involves correctly labeling graphs. And that's a skill unto itself. So I thought I would grab several questions from old exams. If your challenge is graphing, I made a separate video about that and you can watch that. But let's assume we can draw these graphs and we can find the intersections, but we're having trouble labeling. So for each one of these problems, I'm going to do a handful from old exams. I'm going to draw the picture twice, and I'm going to talk about how you can label it in terms of X and how you can label it in terms of Y. So first, let's draw this line. And one comment I made in class as well, you could, at the beginning of the problem, get everything in terms of the variable you want, meaning if you're going to do it in terms of X, you could solve for everything in terms of X. If you're going to do it in terms of Y, you could solve for everything in terms of Y. So that's something you could do sort of systematically no matter what. But honestly, it's faster to figure out the region, what the region looks like first, and then decide. So anyways, we need to graph these things. We need a line with slope a third. I'm not trying to be that accurate. I just need something to work from. And we need the square root function. Square root. Okay, now we're going to label that region that's between them. And I talked about how there's two ways, and let's grab the intersection as well. I believe the intersection's at, let's see, when X is 9, Y is 3. So this is 9, this is 9, this is 3, this is 3. Okay, so my advice, this is how I personally have tried to focus students in recent years, is to label a random point between 0 and 9. So somewhere between 0 and 9, label that X. And we're trying to find a pattern based off of X. So we're thinking, formally, we're thinking for any X between 0 and 9, what is the pattern for how far it is to walk to get into my region? So if I start walking out, I eventually will hit that point. And then I'll eventually hit that point. So we're looking for two Y values, what this Y value is and what this Y value is. And we basically want to say X is going to be between those two Y values. So this is really about labeling. And if we know how graphs work, that's not a problem. But I find that people have varying degrees of experience with this. So this should be the square root of X, and this should be 1/3 of X. Those are those distances when you're labeling. And you can test it out. For example, when you plug in a 9 to here, you get 3. That makes sense because it takes 3 units to get out to that intersection. When you put a 9 here, you also get 3. When you put a 0 in, you get 0 because you're already in the region. But it's more interesting for stuff in between. So if you put a 4 in, you're going to get 2. Let's just do an example here. When X equals 4, you're going to get Y equals 4/3. That's how far it's going to be to go from there to there. And you're going to get Y equals the square root of 4, which is 2. So from here to here will be 4/3 to 2. But the point is the pattern works no matter where you are. So we talked in class first about the area between curves. And we said if you're doing this in terms of X, we want to know how far apart those are. So it's the square root of X minus 1/3 X. That's the labeling. So if you're still kind of struggling with how to label a graph, a function tells you how far it is to go out to your graph. And I find that sometimes people don't realize that. So if this is X, this is the square root of X. That's what that means in that order. And if you give an X, then you can go 1/3. So that's it. If we're going to label in terms of Y, for each of these, you could stop ahead of time and try to label it. I'm going to label a random Y. So for any Y between 0 and 3, I would like a pattern for how far it is to walk to here, and then how far it is to walk to there. And ultimately, I want that length if I'm doing an area question. So that's quick, but you have to label correctly. When we're asking this, we're asking what is this X coordinate based off of Y, And what is this x coordinate based off of y? So you have to use the equations this way because I'm giving you a y value and I'm asking how far do I walk? And you should see the smaller one is y squared because smaller means closer to the axis. So smaller is y squared, larger is 3y, the line. Both these integrals give you the same thing and both of them give you the area. Let's do another one and I'll try to say this a few different ways. Those are the two ways to get the area of that region. They're both correct. They both would have given you the correct answer on the test. So here's another one from an old exam. It says, consider the region bounded by e to the x, y equals 0. Find the value of a such that the vertical line divides. So we don't not necessarily have to do the question, but let's just talk about labeling. So if you're given this picture, I'll just draw it once and then we'll think about it. So there's y equals e to the x. It actually keeps going and there's an asymptote over here. I don't need that for this question. Here's 2. This question is asking about this area. Now here's a good example of one where there's a certain variable we'd much rather use. So I'm going to draw it twice so you can compare. And look at this. But let's just do some labeling. So same game. I'm going to label this x. And let's just focus on that first. So if that's x, how far is it from here to here? What's the pattern? That's e to the x. That's what this y coordinate is. If you were to label it x, y, the y would be e to the x. I'm just trying to say it a number of different ways. And that works over the entire region. Notice it doesn't matter if we were standing here, it would go all the way up to e to the x, or if it was here. It's the same pattern over the entire region. So if I wanted this area, that's probably the easiest way to do it. From 0 to 2, it's always e to the x minus 0, or just e to the x. If you wanted to do the problem in terms of y, it actually is a little bit harder. Because you can see that sometimes you're going from 0 to 2, and then if your y gets up here, you're going from this function to this function. So it changes. There are two distinct patterns. How would we do that? Well, what we would say is for 0 less than or equal to y less than or equal to 1, I think that's where this is, the x goes from x equals 0 to x equals 2. That would be one pattern we're spotting. And if we were setting that up as an integral, it would look like this. The integral from 0 to 1 of 2 minus 0 dx. And that would find the area of this box. You really don't need calculus to do it. It's just going to be 2 times 1, which is 2, which is exactly what this is. But that's not the whole problem. Then you would say from 1 to wherever this is, e squared, which isn't nice. You're now between this dot and this dot. The top dot is still 2, the one that's further away. If you walked from here to here, it's 2. But the question is, how far is it from there to there? And you can't say e to the x because I'm giving you a y. And so you need to rearrange this and say x equals log of y. And so this is log of y. Oh, I didn't even see my typo. We're doing it in terms of y. So apologies if you're worrying about that. You compute that and then you'd add those two together. And it should give you the exact same thing as this. I talked in class about this is why we want options, because there's going to be times we'd much rather do it one way or the other. In this case, I'd much rather do x because the top and bottom don't change. In terms of y, the left changes. Okay, let's do another one. Let R be the region bounded by y equals 3, and the fourth root function, and x equals 0. Okay, this is one where you could do it either way. Maybe I'll see if I can find a more interesting one for the next example. But part of the reason I'm emphasizing this so much is we're going to use this in the next section quite a bit. And so let's talk about this. So if this is x, and you walk out, the first thing you encounter is 3/4 root of x. And if you walk all the way out, it's 3. So if you were doing this to find the area, you would say 0. You'd have to find the intersection. Looks like this is 1. 0 to 1 of 3 minus 3/4 root of x. Done. If you want to do it in terms of y, which is perfectly fine, you would do the integral from 0 to 3. And I would say, if I give you a 3, how far is it to there? And so now we got to rearrange. We would need to solve. So we would have to divide both sides by 3. And then do the 4th power. So it would be y over 3 to the 4th. Or y to the 4th over 3 to the 4th. It's really easier if you simplify. 3 to the 4th is 81. So this would be y to the 4th over 81. I should have said something, but that's the further one. The left side is just 0. You don't have to put that. But there you go. So this, if I was going to label this, this is x equals y to the 4th over 81. And this is x equals 0. If I was to label this one, it's y equals this, and y equals 3. So we're saying for a given y, how do I label where to start and end? For a given x, how do I label where to start and end? Okay. I'm going to add something to this problem. Let's consider the region. So now we have a cubic. We have x equals 2. So we have x equals 2. And now I have a few questions for you. So in the next sections, I'll draw it again. I don't know why I'm using all these colors. Cubic, x equals 2. Okay, so in the next section, in section 6.2, we're going to ask different questions. We're still going to label in the same way, but we're going to have questions that talk about different distances. We're actually going to do like the area of a cross section. We're going to rotate around a given axis. And I know that sounds scary, but it's actually not that bad. But we're going to draw various things, and some things will represent, like we'll say here's a cross section, it's a circle. Later we'll talk about here's a cylindrical shell. We'll talk about that. Don't worry about that today. That's for another day. But there's a reason I wanted to bring it up now. Is the challenge that we'll face is labeling, and that's usually where people run into trouble. So the problem will look like this. It'll say, I'd like to do this in terms of x. It's 0 to 2. It's dx, like we've been doing. We're labeling this x. But what we're going to ask for instead is, if you did a cross section and you got this circle, what's the radius? And then we'll say, well, it's going to be pi times the radius squared. But the radius is how far it is from here to here. So first you have to understand that. But second, you have to be able to label. So do you know how far it is from there to there? What's the pattern? It's x to the 3rd. And filling these things in is this mistake I see students make. And it really doesn't have to do with the method. This one's going to look like this if we're doing it same problem but in terms of y. It's going to be 0 to 8. It's going to be 2 pi times y dy. And the thing that's going to go here is going to have to be this length right here. So in order to figure out that length, you're going to be faced with the following challenge when you get there. Is you're going to have this thing's labeled y, you're going to walk out, and you're going to need to label this, and you're going to have to subtract to find that length. So the question is, how do we label those? So we have the function y equals x to the 3rd. If you solve for x, it's the cube root of y. That's what this is. This is the cube root of y. That's how far it is from here to there. And if you want to know how far it is all the way out, that is 2. And so if you want to know the length between them, it's going to be 2 minus the cube root of y. And these will end up being the same. We'll talk about that. But you can see that if you can't label your graph, you're going to have a real hard time there. Because besides labeling, you're going to have to be able to use those labels in the correct places. So we'll talk about that quite a bit. Here's another one. Let's do one more. So that's what's coming. We'll finish with this one. So we'll do x equals, it's going to be 2 minus y squared. X equals y. This is like this. Sad parabola in terms of y. And then we have the line y equals x. There we go. And let's say we're talking about this area. So we'll get back to talking about area. This one's a little more interesting because there is a certain approach that I think is a lot better, but let's talk about both approaches. I'll do that again. Here it is. Oops, I should have done a better job. Here we go here. Here I have this line. We want this area. Okay, if you do it in terms of x, that's much harder. So if I label an x and I say how far is it to get here, and how far is it to get here, we can label those, and we would label them y equals something, and y equals something, and you'd have to solve. Now one of them is y equals x, that's not bad. The other one is y squared equals 2 minus x, and then you'd have y equals plus or minus the square root of 2 minus x. And the plus would be the positive side, and the minus would be the negative side. So at this moment I realize, if I'm doing it in terms of x, I have to split this up. And points up here satisfy y equals the square root of 2 minus x. And points down here satisfy y equals negative the square root of 2 minus x. And points here satisfy y equals x. So this is bad news. The reason it's bad news is from here to here, I'm between the line and this lower half. But once you get past that mark, it's between these two things. So you'd have two different problems if you were doing the area. For a while, it's between, the pattern is x minus negative the square root of 2 minus x. And then for a while after that, the pattern is square root of 2 minus x minus negative the square root of 2 minus x dx. And that's right here when you're between the upper and lower part. So you'd have to find the intersections. I think we know that the end of this is at 2. So that's 2. And we know it starts, actually we don't know where it starts. So you'd have to figure out what this is, and what this is by doing intersections. So at some point you'd have to do that and doing this problem, because we can do it real quick. Y squared plus y minus 2 is 0. I think these factor. Y plus 2, y minus 1 is 0. Y equals 1 or y equals negative 2. So this must be when y is negative 2. And this must be when y is 1. If y is 1, x is 1. So this is negative 2 to 1, and then 1 to 2. That's one way to do the problem. I wouldn't want to do that because the top changes. So just if you're walking from left to right, you can see it's blue to pink, blue to pink, blue to pink. But then you have this region where it's orange to pink. It changes pattern. So it's much easier to do this problem in terms of y, because if I give you a y, it's always going to be blue to pink, and that's it. It never changes. It doesn't matter if you're down here or here or here. So if you're doing it in terms of y, it's the same pattern for the whole time. So from negative 2 to 1, it's the exact same pattern. It's going to be right minus left. So what is that and what is that? So we need x equals whatever that is. We need x equals whatever this is. So x equals y. And then x equals 2 minus y squared. I solved this for x. Done. That's much easier to do. So, but it's really about labeling. So hopefully, maybe we'll do one last kind of large picture, make sure we're good on the labeling here. So if I took this problem, I have a parabola, y equals x squared. I only drew the positive side because we know we're going from 0 to 6. So the things I want students to be able to do at this moment is label this x and label that x squared. We need to be really comfortable with that. And on the flip side, same graph. I want you to be able to label this y and label this square root of y. Very critical that you understand those are all given by this. And you can always test your, what's going on. Like if I give you y equals 4, then this ends up being 2. If I give you x equals 2, this ends up being 4. That's what we want. And then you do the same thing for the other graph. So now you have another graph. And that one, if you go from here to here, is 6x. And this one, if you go from here to here, is 16y. And that's it. So we're always trying to find a pattern based off of whatever our variable is. If you want me to finish this one, let's see, if we plug in a 6, we get 36. So the two answers would be 0 to 6, top minus bottom. That would be one way to do it. Or you would do 0 to 36 if you're doing it in terms of y. Right minus left. And it's good to keep practicing computing. Both of those should be the same, so it's kind of nice. If you had a test and you had extra time, you could do it the other way if possible, if it's easy to do. And verify you get the same thing. Okay, I hope that helps and gives